All right, to finish up this section on geometric series, let's do a couple examples. And I want to start off with one of the most interesting uses of geometric series. So the example here is we want to show that 0.99999 so on is equal to 1, right? So just like 1/3 is equal to 0.3333 forever, we can show that just 9's repeating forever is equal to 1, right? And this is the procedure behind how you show any of these infinite repeating decimal expressions is equal to, or what fraction it's equal to. So let's look at this. The way we can approach this is as follows. All right. So this is 0.999999, right? We're going to break it into numbers like this. And further, what we can do, actually, yeah, let me make that statement more apparent here. So the reason we did that, I'm trying to say that 0.99999 so on is equal to this sum. Right? Here, look at this as 9 times 0.1 plus 9 times 0.01 plus 9 times 0.001 plus 9 times 0.0001, right? And so on, right? I want to recognize this as a geometric series. Hopefully you can see here, this is the series sum from k equals 1 to infinity of 9 times 0.1 to the k. Right? Now, you'll notice here, this doesn't quite start at the same place as a geometric series does, right? Geometric series needs to start at k equals 0. So what we can do is say, all right, well, I'm going to make this series start at 0. Okay. But if we add in the k equals 0 term, that's something extra. So we want to make sure that we subtract that back out. So if we plug in k equals 0 here, we're going to get this term, right? So what we want to do is, we're just making sure that we're not editing anything. So actually, maybe let's do this here. So what we're doing here is we're saying, okay, well, let's add in 9 times 0.1, 0.1 to the 0. I want to add that term in, because if I add this to the series, that gets me here. But I can't just add something without changing the expression, so I'm going to subtract it back off. Right? This is the trick called adding 0. Right? And this is something you've probably done before at some point when completing the square, for example. All right. So if we can find, actually, let's simplify this. This is k equals 0 to infinity, 9 times 0.1 to the k minus 9. Right? So if we can find the sum of this geometric series here, we can figure out what our fraction is going to be, right? So here we should just double check that everything makes sense. So here a is 9, this number is a. R, the ratio, is the thing to the kth power, right? Notice here, absolute value of r is in fact less than 1, so this does converge. And we know that it converges to a over 1 minus r. So a over 1 minus r. and then minus 9. So this is 9 over 1 minus 0.1 is 0.9. Right? So this is going to be 9 over 0.9 is 10 minus 9, which is 1. Exactly as we said it would be. All right? So this is one neat thing we can do with geometric series. We can handle these repeating fractions. These repeating decimals. Right? Let's look at a couple more examples here. Right? All right, let's look at the series k equals 0 to infinity of 3/2 to the k. So let's look at this. Does this converge or diverge? If it converges, what does it converge to? Right, well here, a is 1, r is 3/2. Okay, so here r is greater than or equal to 1. Right? Since that's greater than or equal to 1, this diverges. Right? So, that's great. Right? Let's do one more just to round this off. Let's say we look at the series k equals 0 to infinity of 2 over negative 3 to the k. Right? Let's look at this series here. We need to figure out what is a and what is r. So first things first, when we're dealing with one of these geometric series, we want to pull out the parts that don't have a k. Right? So if we pull out the part that doesn't have a k, we're looking at something like this. Right? It's very important that this negative sign be inside parentheses here. Right? All right, but I'd really like to have, some number to the kth power, not 1 over some number. Well, the good news is that, 1 is equal to 1 to the kth power, right? So there's no harm if I write this. All right, let me get rid of this now. Right, because again, 1 is equal to 1 to the k, so it doesn't matter here. And now that the top and bottom both have kth power, right, we could write this as 1 over negative 3, or negative 1/3 to the kth. So here, a is 2, k, oops, sorry, not k, r, maybe I'll do this underneath. A is 2, r is negative 1/3. So the question is, does that converge? And the answer is yes, it does converge, because absolute value of r is less than 1. So this converges to a. This converges to a, which is 2, over 1 minus r. Right, so that's 2 over 4/3, which is 6 over 4, or if you like, 3/2. And there we go. That's all there is to it. So all geometric series come down to is just being able to sort of pick out what is a and what is r, and then compare that to whether or not the function should reasonably converge or not. Or sorry, not the function, the series. Right? Compare that to our test up here for geometric series. Right? And that's that.